The 21st century seems to be a challenging period for our wonderful planet Earth. Climate change and increasing air pollution are two out of many serious threats we are facing. The sixth assessment report of the Intergovernmental Panel on Climate Change, which was published in 2021, stated that the range of total human-caused global surface temperature increase from pre-industrial time to now is about 1.07 degrees Celsius. Carbon dioxide and methane are the two main drivers of the warming. Most of the atmospheric aerosols are counteract the temperature increase and cool the planet, partly by direct scattering incoming solar radiation or by acting as a surface where water molecule can condense on to form cloud droplets. Clouds are then reflect the incoming solar radiation back to space and in this way have a cooling effect for our climate. It is important to know that under the atmospheric conditions, water molecules will not form a cloud droplet without aerosols, as the required saturation vapor pressure of water, so the existing amount of water molecules per volume is much too low in the atmosphere. In this way, aerosols are crucial for clouds and precipitation and have a strong impact on our weather and climate. However, the impact of aerosols on climate still involves the highest uncertainties in predicting how temperatures will change in the future. Concerning air pollution, the poor air quality nowadays represents one of the largest risks to health, causing several millions of premature deaths every year. This makes it the top environmental mortal risk, much higher than the polluted water. Ultrafine particles in the size range below 100 nanometers, so about 1,000 times smaller as the diameter of a hair, pose a serious health risk, as they enter the body mainly through the lung but are located within the body to accumulate in all organs, including the brain. To improve air quality and to ensure we know how future climate will evolve, it is important that we achieve a comprehensive understanding on the sources, transformation processes and sinks of atmospheric aerosols. The first question we must consider is, where are these atmospheric particles coming from and how atmospheric chemistry is involved? In science, we differ between two sources classification: primary and secondary aerosols. Primary particles are released directly from the Earth's surface. They be natural, like for example sulfur particles through volcanic eruptions, or dust particles blowing up from sandy grounds by wind. They can also be anthropogenic, for example when you heat up the sauna with wood or make a nice campfire. Primary particles contribute a major fraction of the mass when you sum up all atmospheric aerosols, but their number concentrations are comparable with the secondary particles. Most of the primary particles are quite large, which means they will not go deep into our respiration system. And also they are dominant when you measure the aerosol mass at one place. The health effects are limited. Secondary particles are formed directly in the atmosphere by molecules from different origins. This could be natural sources coming from trees and plants. You can smell them when you walk through the forest. And we call them bioorganic volatile organic compounds. Or they can have anthropogenic origin, for example through combustion process, like exhaust emissions from traffic. Most of these molecules will not participate in the aerosol growth directly, as they are volatile and want to stay in the gas phase. However, chemical reactions will change their volatility, and then these somehow new molecules can participate in the formation and growth process of atmospheric aerosols. Secondary particles can have a strong impact on our health because of their small sizes and their locally high number concentrations. They also contribute significantly to the cloud droplet formation and are observed nearly everywhere. My research during the last decades was and still is on the secondary aerosols. Mainly when and under what condition molecules form an atmospheric particle, which molecules are involved, and how atmospheric chemistry creates these molecules. Here the chemistry plays a major role in changing the physical properties of a molecule from being volatile to a molecule with a very low or extreme low volatility. This is not straightforward, as we must consider a huge number of chemical reactions in the range of tens to hundreds of thousands, and many reactions are still unknown. Only 8 years ago, in 2014, scientists from the University of Helsinki, together with other colleagues, discovered experimentally a new type of molecule with immense influence on the particle formation process. However, the exact chemical path, so how these molecules are formed, was still unclear. To tackle this, we established in the last years, in cooperation with several other groups, new chemical schemes to predict how these very crucial molecules are formed in the atmosphere and evaluate the new chemistry, first for various chamber experiments and later at different environments, like the boreal forest. Next, we implemented these new schemes in our different atmospheric aerosol models and investigated how strong the molecules contribute to the formation and growth of atmospheric particles. Hereby, we also estimated with different methods the physical properties of each new molecule to calculate when it will transfer from the gas to the particle phase. The results, the new chemistry schemes implemented in our different models, improved our ability to calculate the formation and growth process of secondary particles dramatically. So we can say that the identification of these new molecules, the creation of the chemical paths, and finally the applications in chemistry transport models was a breakthrough in atmospheric chemistry and aerosol research. This now improves our ability to investigate under which conditions secondary particles are formed and how this will change in the future, in case anthropogenic emission patterns change or higher temperature affect the emissions of the biosphere. During the last decades, atmospheric scientists, including my group, improved our knowledge on the chemistry and aerosol formation process immensely. However, there are still many open questions, and we are far away from a complete understanding of these complex topics. Sometimes it seems that as more knowledge is gained, more questions arise, and including all these new findings creates even more complexity in our chemistry and aerosol models. Also, we are operating our models on supercomputers. We are facing more and more computational limitations. Means the complex chemistry and aerosol models are requiring long times to run and are too time demanding to apply them directly in regional or global scale models. For instance, Earth system models, which are applied to make future climate predictions, split the Earth's atmosphere in millions of grid boxes, and the chemistry and aerosol dynamic must be calculated for each grid box. This makes it nearly impossible to apply detailed chemistry and aerosol codes in such models, also when using the fastest available computers. For this reason, Earth system models normally apply very simplified parameterizations to calculate atmospheric chemistry and aerosol dynamics, which involves additional uncertainties. Nowadays, we started to step forward and use machine learning and artificial intelligence techniques to overcome this problem. We first apply our new and detailed chemistry and aerosol knowledge and create huge training datasets, which are then used to build neural networks. These neural networks, when trained for all possible input data variations, will then produce the same output as the detailed codes, but more than 1,000 times faster. In the final step, the neural networks could be applied to regional weather forecasts as well as air quality and climate predictions. In this way, we would include all our knowledge in atmospheric chemistry and aerosol dynamics with feasible computational times. Summing up, atmospheric aerosols are crucial in cloud formation and have a serious impact on our health. An important fraction of these aerosols are secondary particles, which are formed by molecules with precursors from natural and anthropogenic sources. Here, atmospheric chemistry has the key role when changing the physical properties of these original emitted volatile compounds to low or extreme low volatility. Afterwards, these new molecules can participate in the formation and growth processes of secondary aerosols. On one side, our current knowledge concerning atmospheric chemistry and aerosol dynamics has immensely improved in the last decades. However, a comprehensive understanding has still not been achieved. On the other side, we are facing more and more computational problems when we want to add our new findings in large-scale models, which are important to predict our weather, air quality and climate. So the applications of artificial intelligence technique offer a possibility to overcome the computational limitation in the future.